You hit a pothole, the whole car dips, and then, for a second, it settles. It doesn't bounce 5 times like a trampoline. It sags once, maybe twice, and it's done. That calm, quick settling is a tiny piece of math bolted into every wheel. It's called a shock absorber. And what it really is a machine for killing oscillations. Here's the model. A mass on a spring, but this time with friction. A damper. Mass times acceleration, plus a friction term, plus the spring pulling back, equals whatever force you push with. In the free case, with no push, the whole story hides inside one small equation. Let's clean it up. Divide through by the mass and 2 numbers pop out. Omega naught, the natural frequency, how fast the spring wants to bounce on its own. And P, the damping coefficient, how hard the friction fights back. Everything comes down to a tug of war between these two. To solve it, you write down the characteristic equation, and the answer is a pair of roots. Minus P plus or minus the square root of P squared minus omega naught squared. And that little thing under the square root, it decides absolutely everything. So watch the sign. If friction wins, P bigger than omega naught, the root is real and nothing oscillates. If the spring wins, P smaller than omega naught, that square root goes imaginary, and imaginary means wiggle. 3 cases, 1 sign. Case 1. Light damping. The soft, springy case. The mass swings back and forth at a frequency called beta, the square root of omega naught squared minus P squared. But every swing is smaller than the last, squeezed down by a fading exponential. It rings, and the ringing dies. Case 2. Heavy damping. Now the friction is so strong, the mass never even makes it past the middle. 2 real roots, both negative, so it's just a slow, tired slide back to rest. No overshoot, no bounce. Think of a heavy door on a good hinge, easing itself shut. And right on the knife's edge between them. Case 3. Critical damping. Exactly enough friction that the system snaps back to rest as fast as it possibly can without a single overshoot. And that, right there, is the sweet spot your shock absorber is tuned for. Okay, that's the car settling on its own. But the road never leaves it alone. It's a constant string of bumps, a force pushing at some frequency omega. So now we drive the system. And ask the scary question, can we make it blow up? Here's the beautiful part. With any damping at all, the answer is no. Because P isn't 0, the driving frequency can never exactly match a root. So the runaway, infinite resonance of the frictionless world is just gone. The response always stays bounded. Friction, even a whisper of it, saves the system. The steady vibration has an amplitude, and it's a fraction. Constant force on top, and on the bottom, this square root. The amplitude is biggest exactly when that bottom is smallest. So the whole game is find where the denominator bottoms out. Grind through the algebra, it's just a parabola in omega squared, and the denominator bottoms out at omega equals the square root of omega naught squared minus 2p squared. Look at that, not at omega naught, a little below it. The peak amplitude sits just under the natural frequency, pulled down by the damping. And now, the whole picture. Crank the damping up, and watch the peak do 2 things at once. It slumps lower, and it drifts left, further below omega naught. Push the damping hard enough, past omega naught over root 2, and the peak vanishes completely. The curve just sags. That's your shock absorber, flattening the resonance so your teeth don't rattle. So that's the trick hiding in your suspension. Too little damping, and you bounce down the highway. Too much, and the ride feels like concrete. Critical damping, right at the edge, gives you that clean, single settle. 1 sign, under a square root, splitting soft from stiff, and a resonance peak that friction quietly pulls out of harm's way.